So before we get into more questions on solving exponential word problems, I want to ask you about this question. So what's the quickest way to calculate your new price if you've got your tax with it? So in Ontario, we have a 13% GST, which is on top of any sales that we have. So if you buy something that's $19.99, what's the quickest way to figure out the actual cost? So you could do 13% of $19.99, get a decimal, and then add that to the price. So figure out how much tax you're going to pay and add it to the price. But most of you might be familiar with doing the shortcut way, which is take your price of $19.99 and times it by 1.13. And if you have your phone or your calculator handy, you can quickly just do that multiplication and it will get you your answer. So if we punch that in a calculator, you get something like 22.5887, but of course it'll be rounded to the nearest 2 decimal place because we're talking about money. So the actual price is 22.59. So I imagine some of you have known this before, that the quick way is to multiply by 1.13. The question is why? Why is that? Well, this is actually an exponential growth question. This 1.13 actually stands for 1 plus 0.13. So if you're doing 13%, if you're just doing calculating the tax, you would change that to the decimal 0.13 and multiply it by your $19.99, and that would get you your tax part. Your 1 part is actually your 100%. So this, the 1, is the actual price of it. So the 1 is the 1%, or the 100%, plus your tax, and that's your 13%. And so it gets put together into 1.13. This is actually then an exponential equation. You could do your amount, so your A equals a base to some exponent. Well, our amount is, we're starting with 19.99. Our base then is this 1.13. The 100% is the 1, and the 13 is the 13% tax. And you're only doing this calculation once. If you had to do tax again and again and again, then it would be a full exponential equation, but it's just the one time. So this is your amount, your initial value. This is what's called the growth factor. And this is the time period that's happening. In this case, when you're doing tax, you only have one time period, but in other instances where you have something growing. Now, how is this question different than the ones we were doing before? Well, in the ones we were doing before, the growth factor was always 2, because we were talking about stuff that was doubling, like bacterial growth and the doubling time. So that number was a 2, and it was raised to some exponent, however often it gets doubled. So the questions we're going to do today is just going to have a different growth value, growth factor instead of 2. So if we do look at that formula that we had yesterday, the A times 2 to the T over D, that 2 is actually really 1 for the 100% that you have there, plus since you're doubling by 100%. So it's 1 plus 1. Instead of like the tax one where you're only adding 13% on, when you're doubling, you're adding 100% on. So the formula is actually the same formula. The growth factor is just 1 plus 1 to get 100% more, which is 2. Similarly, the half-life is a decay, but now you're not adding it in there, you're subtracting it. So you're taking a half away when you do a decay, when you're doing the half-life. So you start with your 100% and you're taking away half of it. And that's why the 1/2 actually comes from 1 minus 1/2. So the concept that we're doing today with a growth factor or a decay factor is actually not different. It's just the first set of questions we just had 1 plus 1 or 2, so it was doubling, or 1 minus 1/2 and our half, and just doing half-life. But today we're not going to do doubling, we're going to do a percentage. So when you're talking about what your rate is, your rate of growth or your rate of decay, it's your base now becomes, if it's a growth one, 100% plus whatever the growth factor is as your percent. So for the first example, if it's a 6% growth, so it's like 6% tax, well, we would have the 100% plus the 6% to get 106%. And then that would, when we actually use that, that would go to the decimal 1.06. Okay, the 6% is 0.06, and so added to 100%, and your growth factor is going to be 1.06. Now, you probably wouldn't write down all that stuff. In this one, 1.5%, well, that is 0. If it was 1%, it'd be 0.1, but it's 0.15, so that's what that percent is. So your base now is 100 plus that, so 1.015 would be your base. See, this one here was 0.06. So 1.5% is 0.015. 0.5% is even smaller than that. It's 0.0, that would be 1%, but we don't want that. So it's half of that. It's 0.005. And so your base would be 1.005, would be a growth of 0.5%, something growing very small. So there's your how you calculate your growth factor. The decay factor then is if you are having something getting smaller and you've got a fraction here, you've got to take away your take away from the 100%. So if it's 15%, 15% is 0.15, close to the 13% tax, but this time we're doing 100% minus the 15%. So that's 85%, which would change as a decimal as 0.085. And that kind of makes sense. If you are taking away 15%, you are actually only getting 85% of the original. So if you do 85% of the original, that's how much you'd have. If you had $100 and you're taking away 15%, you're getting 85% of 100, so you're getting $85 is 85% of 100. 4%, okay, the biggest mistake I see is people say it's 0.4. That's not right. That is 40%. For 4%, it is 0.04. Again, we get this by dividing by 100. And so our base is going to be 1 minus 0.04, or 0.96 is our base. 100% is the 1 minus the 0.4, or 0.04 is 96. 5.1, 0.051. We're going to do 1 minus that. And that one might need your calculator, but it ends up being 0.949. Just confirming that on my calculator. Did that in my head. I'm pretty confident of it. 0.051. Yeah, 949. I was just sort of taking away 5% in my head and then 0.1% more to get the base is that. Okay. So that'll pop up in the questions we're doing today, but you'll see that the questions are very similar in the math that we answer, but the bases will be different. Yesterday's questions only had 2 as the base when it was doubling, or half as the base as if we're doing half-life. So here's our first example. You can pause the video if you need to copy that down, but I'll just give you a second to write it down. So it says the population of a third world country is 3 million people. If it is increasing by 6% per year, estimate the population in 5 years. So we're still going to use the similar formula from what we did yesterday, but this time we're going to have y equals a is your amount, but now the base is going to be a b or some growth factor. Okay, so whatever the base is, to the power of time. So how often are you doing this? How often are you doing your percentages in this particular case? So it's similar to what we had before, except yesterday it was a times 2 to the power of your time, or the number of doubling periods. Here it's going to be a growth factor. So first thing we should notice is if we're growing, this is increasing, so we know it's a growth factor. So that means it's 100% plus the 6% growth. So this is going to be 1.06 is your base. Your amount, so this is your base, or your growth factor. The amount starts with 3 million. And our time is over 5 years, because it's going to be 1.06 every year per year. So we have to do this 5 times. So it becomes 3 million times 1.06 to the power of 5, the number of times that you're calculating this increase. So as we said yesterday, make sure we go to BEDMAS. So if I went to my graphing or my calculator here, I'll turn it on. Depending on what type of calculator you have, oh, it's not turning on for me. There we go. So you could maybe type this all in depending on your calculator. I'm going to pretend that I can't do that, so I'm going to do the exponent first. That's what BEDMAS tells me to do. So 1.06 raised to, or to the exponent 5, gets me that decimal. I'm not going to write down that decimal. I'm just going to multiply it by 3 million. And in one step, I'll get my answer of, oops, let's do this. So I can see both. So that's 4 million and 14,676. 4,014,676.733. Since we're talking about people, I think we should round that to the nearest person. Doesn't make sense to have a decimal answer there. So then my answer is 4,014,677 people. And since this is an English question, we'll finish with a quick English answer. In 5 years, there will be just over 4 million people. Okay, so now let's go big screen here. And we'll move on to our second example. Again, I'll wait a second while you copy that down. So I find these questions a little more interesting because they're a little more practical to our real life. The questions we've been doing lately have been like bacterial growth or radioactive decay, something we probably won't come across too often in our actual life. But this is something we will. Hopefully we would be saving some money and earning some interest. And this interest is compounded, which is an exponential of idea. And so we'll want to use our exponential formula to try and figure out this answer. So it says you've been saving money for 2 years and an interest of 0.5% per month. Not great, but if you're just keeping it in a savings account, there's not a lot of interest earned in a savings account. This is probably actually more than you would get in a savings account. But here's how much you have right now. The question is, how much did you have 2 years ago? So again, we're going to use the same formula. This is going to be a growth because we're gaining interest. So the growth rate to the power of time. But we've got to interpret our question. So we've been saving for 2 years. So our this is 2 years. But I'm noticing that my rate is in months. So I think I need to change this to 24 months. Okay, that's going to be, we need to be in the same unit in order to do this. It says we currently have a certain amount of money, which means I don't know what I had at the beginning, but it has turned into $536.58 in this 2 years or 24 months. And the rate, well, it's a growth of 1 plus the 0.005. It's 0.5%. And so my rate is going to be 1.005, 0.5%, 0.5%. Again, if you need to remember that, when you're going from a percent to a decimal, just divide it by 100. So 0.5 divided by 100 is 0.005. All right, so if we plug this in into our formula, then we know what our answer is. What we don't know is how much we had at the beginning. We know the growth rate is pretty small at 1.005. And the time, well, this happened 24 months because we got that interest every month for 2 years. All right, so now we got to go to our calculator. So let's see if this will work. If I put it back there, yep, that looks pretty good. So I'll turn it back on. Clear that out. So again, I need to do this decimal first. So it's 1.005 to the power of 24. That's going to get me some big long decimal. If you want, you could write that down. So I'll write it down. 1.127159776. Don't round that number. Don't round. Okay, we don't want to estimate our percentages, our interest. The bank certainly doesn't. You want to keep as many decimal places as possible. That's why it's not necessary that you necessarily write it down, because you might be tempted to round it. But I want the A by itself. So I'm going to have to divide it by this big long decimal on both sides. Now, hopefully you have a way to divide by an answer so you don't actually have to retype this. For me, I can go 563.58 divided by, and then I have an answer button right here in yellow, so I go Shift Answer, and it'll take that full thing. If you don't have an answer button, you might have a memory feature. You can store that number in your memory, because your calculator actually displays a lot more than the decimals that are there. So if we were able to keep as many as we can, then we get an answer of, oh, not surprisingly, it worked out to 500. And again, we'll round this to one decimal place, so it's almost exactly 500. So therefore, you invested $500 2 years ago. All right. And then we just have one more example to get through. So again, I'm just recording this in between classes, and a bell just rang, so I'm going to have to just go through a little bit quicker than I normally would. But in this third example, it says a car's value depreciates by 15% per year. A dealer sells a 6-year-old car for $6,500. What was the original price? So cars lose their value when you drive them off the lot. They lose a lot of value. A used car obviously is worth a lot less than a new car. That's why some people only buy used cars, because of how much it depreciates. And even after the first year, you lose a lot of its value. But it is a decay, so it's a depreciation is a decay. So this time the formula is going to be y equals a, and this is going to be a decay rate, still to the power of x. So you want to figure out how many times we're doing this. So I'll just move this over here. So looking at this, it depreciates by 15%. So this time the decay rate is your 100% minus the 15%, which is 85%. You might do this as 1 minus 0.15 to get the 0.85. All right, so that's your decay rate. Here we know in 6 years he sells it for that much, which means we don't know what the original was, but we do know right now it's only worth $6,500, and our time has been 6 years. So the $6,500 is where we're at now. We're going to have to work backwards to figure out the A. The decay rate then is 1 minus 0.15, or 0.85 to the power of 6 for 6 years. Again, if we go to our calculator here, so this time it's 0.85 to the power of 6. Again, you may choose to write this or not. Again, you're not rounding, so writing it down might seem a bit of a nuisance. We know we have to divide by this. Don't divide by 3.77, divide by your answer so you have the entire thing. So we're going to go 6,500 divided by my answer to get that it costs $17,234.54 if we round it. So that means the original value of the car was $17,234.54. It's not very expensive these days for a car, but that's what we have here. Okay, so hopefully you can understand those questions and you've got a good sense of what's going on. Your practice then is on the worksheet, numbers 9 to 13, so it's on the same worksheet as yesterday. It's just the bottom questions at the bottom of that sheet. Good luck.